Today I worked on basically figuring out the topology. Yeah, it is topology. It's not just geometry of the Tesla valve. So the Tesla valve that I'm working on is going to be a branching structure Tesla valve. So it's going to have one big central impedance. In electronics, Tesla valves are essentially diodes. And what we want is diodicity. Diodicity in this case is flow in one direction and resisted flow in the other direction. So you want that ratio to be as big as possible for flow to move easily down one pipe, and then when it's going back up the other way, it gets resisted a great deal. The bigger that difference is, the better. And I'm just going to see how much, a regular Tesla valve is leaky. Even if in the resisted flow direction, it's not like a ball valve, which can totally seal off the flow, depending on how strong the ball valve is. So I'm trying to get it to where it seals off an intense amount of flow, that it just resists like no tomorrow. And that probably requires optimization beyond trying a tree structure, but I'm curious to see how much a tree structure gets me. So I'll probably be making two Tesla valves, one that's sort of the normal Tesla valve to compare against, and one that has this tree structure. And part of the difficult part will be getting them to be characterizable so that they'll be similar enough so that I can look at the different outputs and be like, oh yeah, it's doing a much better job, or it's doing a far worse job. And today that just meant more drawing. I did some CAD, but I realized like the drawings are really where I'm deciding things. So the two architectures that I was thinking of doing are on this side. It's better. So here we have a single lobe, I'm going to call it. So the flow can go down that pipe, and can intersect into the middle. So it's almost as if I've taken one Tesla valve, if we ignored this pipe here, and then flipped it onto the other one, and that, I don't know if that's going to work. I assume this is going to cause some weird sort of like pseudo Helmholtz problem where it'll be like shuttering between the two sides, or it'll just go down one side and you'll have very little flow in the other direction, and you'll get very asymmetrical behavior down the tree structure. So as it goes on to the, if we get flow here, but not here, anything that's on that branch is going to be active, and here it's going to just be a waste of space. So I think I am converging on this sort of heart-shaped structure here, which looks far more like a Tesla valve on one side, just flipped to the other side. There's no overlapping in this case. And so each side will get a flow to cause resistance, and each side can then pass to its next branch. And then we'll have another branching structure just like this one, but a little bit smaller here, and then further up a little bit smaller. I think I'm going to do 3 stages and see how they go. But the first stage, what's really going to happen is the first stage is going to be this one. This is what I'm interested in the most. So we're just going to have a single section and run that and see how it behaves. And then we'll see about adding more and more. So that's just going to be a 3D print with a, what's it called? Sort of a Ninja Flex gasket that goes up against the acrylic plate. And that should give us a good view. Maybe I put dye in there and pour liquid through so that we can see how it's behaving. See if it collects in one region or whatever. A lot of times when people make Tesla valves, it's very naive. So I'm adopting a naive approach in this case. My angles here are arbitrary, but your angles do matter over the direction you spray water back into the flow to cause resistance, and how much, like, the angle of the flow channel versus the angle of the U-turn that's happening. All that does matter to the flow. So I'm just kind of taking angles very similar to Tesla's patents. You see that online with other people who do exactly the same thing. And that naive approach is fine, but it means that under certain flow regimes, at certain sizes, it's not like it's going to be an optimal resistance. The question for me is just, is it going to be significantly different? I'm looking to see if, how much does it arrest per sort of resistant channels traversed. So I'm looking at different things. It's not, for me, it's never about efficiency. So efficiency can be found after you prove the general idea works. So we'll see how this sort of multi-channel thing works. I was looking at the literature, and I don't see stuff that's very similar to it. There are people who have made symmetrical Tesla valves, and some with very, what I would say is like naive configurations that, I'm using that word a lot, but anyways, configurations that are very simplistic, which are often okay for Reynolds numbers that you get with microfluidics. So you can get some efficient structures out of that. But in this case, we're going to be operating at a significant macro scale. We're not trying to do microfluidics. So that's going to be the next thing, is to just model up the actual CAD and then hit print. So that is, oh yeah, and another thing, I'll probably be setting up the printer in my place. I've been using another printer, but so now I'll have easy access to a 3D printer, which is the iteration rate will go much faster. So yeah, that's where I am along in this particular adventure, and yeah, that's it's just a lot more drawing stuff. It's amazing how much drawing is part of my process. I assume there are other people who don't go into drawing as significantly, but for me, it's just little scribbles everywhere until finally it starts to converge into something that I actually want to make. So, as always, thanks for watching, and be easy on yourself.